Where we left off on Friday, right? We were talking about evaluating limits analytically, and just quick reminder about this, right? So what we always try to do is attempt direct substitution. Okay, it's one of three things is always going to happen when we're evaluating limits. First two make the problem easy. First option is it works. You get a numerical answer that is defined. And so that's your limit. No big deal. Second option, second thing that could happen is you get an answer that's a number that's undefined. It's a number divided by 0, which means that the limit does not exist for now. Later on, we'll be more specific. And here's an example, right? Like if we have the limit of this rational function, x minus 5 over x plus 2, as x approaches -2, when I apply direct evaluation, I end up with -7 on the top, 0 on the bottom. There you go. That's undefined. Does not exist. Okay, the third, and for us at this point, most important possibility, third option is you get something like this. You get something like 0 divided by 0, or later on, it could also be something like infinity over infinity, or it could be something like 0 times infinity, or it could be something like infinity minus infinity. I think that's it. I don't know if we'll even deal with all of those, but for sure we'll deal with that case. I'm going to limit us to just the types of indeterminate forms, and these are other indeterminate forms that show up on the AB, the AP Calculus AB test, not the BC test. This is one of the things I don't like about the AP test is that it kind of forces you to not do, sometimes cut yourself short when I think it's better to look at more stuff, and so again, we'll just kind of make a decision when we get there. If people are still really want to do the AP test, which is great, I encourage that, that's fine. Then we'll limit ourselves. If we're not really focusing on that so much, we're just going to focus on like what would be good for college, and for college purposes, I think it'd be good to at least see all these things so you're introduced to them. But we'll cross that road when we get there. For now, the third option, the third outcome that we could have when we evaluate directly is an indeterminate form. Okay, and that always means more work. Okay, but what kind of more work? Now, there is going to be kind of a secret weapon for this type of outcome when you get an indeterminate form, and that's called L'Hopital's rule. But that's later. We have to know how to differentiate before we can apply L'Hopital's rule. But because we have this secret weapon, I am not going to spend a tremendous amount of time on this section right now, looking at algebraic approaches. I want you just enough so you understand the concept, but we don't need to really be like super experts at resolving indeterminate limits without using L'Hopital's rule, because we'll always just use L'Hopital's rule in the future. Make sense? So, I'm going to abbreviate this compared to what I've done in the past a little bit. So let's start off with this example. We've got the function x squared over x. Is that equal to x? Thumbs up or down, I think. Everybody got a vote here. What do you think? Are they equal? I'm seeing some thumbs up. You get a sense it's a trick question? You're right, it is. They're not the same. They're almost the same, and that's what's important here, right? That's good. Good Scooby sense there. You knew what was going on. I was tricking you. So they are not exactly the same, but they are extremely close to being exactly the same. In fact, this isn't a very creative title. Sometimes in math, we I don't know, we need to be a little more creative, but We would call these functions that agree at all but one point. Okay, they are almost identical, but what value of x has to be excluded from the domain of the blue function, f of x? 0. How come? Can't have 0 on the bottom. So we would have to say for the blue function, x cannot equal 0. Okay. Well, algebraically, if I divide by x, top and bottom, I just get x for an outcome, don't I? Okay. That's what originally when you guys gave me thumbs up, that's because you were saying, yeah, well, I mean, x squared divided by x is equal to x by properties of exponents, right? That is true. Okay. But the function, we'll call it g of x because it is a different function. The function g of x equals x, you will see, oops, is slightly different. What's the difference? Yeah, it fills in that hole, right? Because the domain of g of x is unrestricted, okay? So then how can we use this to our advantage? Well, first of all, whenever you have a function like this, a rational function, which if I try to evaluate the function at 0, notice that I get 0 over 0. There's the possibility that something like this is happening, that you've got this function that has a hole in it, but otherwise it could be simplified, right? Okay, so every place except that one point, the blue and red functions are identical. So we can use that to our advantage. Okay, if I want to know what is the limit of f of x as x approaches 0, you guys can all tell me the answer. What is it? What is the limit of the blue function as x approaches 0? 0, right? The ant anticipates stepping on a y value of 0. You can see that from the graph, right? What if I didn't have the graph there? What then? What would you do? What you would do is you would realize that the blue function and the red function agree every place except at that one point, and we would take advantage of the fact that their limits are the same. And the limit of g of x, I can evaluate that directly. If I plug 0 in, I just get 0. How'd that work? Well, because we know that these two functions are interchangeable except at that one point, we know that the blue function, the ant cannot step there because the function's undefined at x equals 0. But on the red function, where we have simplified the quotient, we no longer have an x on the bottom, and so the ant could stand there. Okay? Now, you got to listen to this very carefully. Here's our logic. If we know that the ant is approaching the point on the blue function where he would actually step on the red function, then why not trade for the red function and use direct evaluation or direct substitution? See my point? Okay. That seems like kind of a complicated strategy, but it turns out that the math gods in their infinite wisdom have created this situation in such a way that when we do the algebra, it just always works out. Okay, I'll show you what I mean by that. Let's look at an example. First of all, just kind of a summary of what's going on here, right? The limit of f of x, or the limit of x squared over x as x approaches 0, is equal to the limit of x as x approaches 0. I just simplified that algebraically. We just did our strategy without even really thinking about it. When we do the algebra of simplifying that quotient, we're trading blue function for red function. We just filled in the hole, okay, which is 0, okay? So to summarize this, to find the limit of a function at a hole, find the function that agrees with this function at all points except the location of the hole, and fill in the hole by simplifying the quotient, okay? what really happened there when we simplified the quotient? Let's look at this in detail for just a second. So the limit of x squared over x as x approaches 0 is the limit of x times x over x as x approaches 0. And all we did was cancel the offending factors. When I say the offending factors, I mean the factor that was causing the indeterminacy. That x on the bottom caused us to have a 0 on the bottom, and let's just say that that x right there caused us to have a 0 on the top. When I cancel out those like factors, the indeterminacy disappears, and I just get the answer, limit of x, which is 0. Okay, let's try it again. I'm going to skip, you know what? I'm going to skip ahead for just a second, just to make a point, and then we'll come back to this one. Yeah, here's a good one, okay? So same kind of thing going on. I've got f of x equals x cubed minus 1 over x minus 1. Okay, if I want to take the limit of f of x as x approaches 1, if I try to directly evaluate, what do I get? When I plug in 1, what's the outcome? 0 over 0, okay? What do we call that kind of a form again? Indeterminate, right? We get the indeterminate form zero over zero. Remember, that always means more work. We have to resolve the indeterminacy. Okay, what's that look like? Well, what it's going to look like is we've got to factor the top and factor the bottom, and we're going to cancel the factors that are causing the indeterminacy. This is equivalent to filling in the hole, as you're going to see in just a second. So what does that look like? Okay, you guys remember x cubed minus 1 is the same thing as x cubed minus 1 cubed. So that's just a difference of cubes, right? Do you guys remember the factoring pattern for a difference of cubes? A cubed minus b cubed factors into what? See if you can remember. Remember, there's going to be a binomial and a trinomial. The first term involves a power of a, second term involves a power of b. So we know that's going to be an a, that's going to be a b in our binomial. In our trinomial, we're going to write all the different ways of finding a product of those two. So a times a times b times b. And how did we fill in, what was our sign pattern? Remember this from Honors Algebra 2? It's been a while. Remember this, what we did if we had a difference of cubes? The sign pattern was same, opposite, always ends on plus. Is that ringing a bell? Remember seeing that? Okay, it'll come back. Once you've learned something, relearning it's easy. So there's our pattern. So this time x cubed minus 1 cubed would just factor into x minus 1 times x squared plus 1x plus 1 squared, which is 1, right? Okay, on the bottom we've got an x minus 1. Okay, look what happens algebraically then in our limit. When we're taking our limit, the x minus 1 factors on the top and the bottom are going to cancel. Okay, those were the factors that were causing the indeterminacy, right? As x approached 1, the value of that factor was 0 and the value of that factor was 0. So once I cancel those, the indeterminacy is going to disappear. Okay, when I cancel those, I'm left with the limit of the expression x squared plus x plus 1 as x approaches 1, which is just 3. Okay? Right? So when we're approaching this algebraically, what's our strategy? It's called a cancellation strategy. We're just trying to factor, when I have a rational function, polynomial over polynomial, if it's indeterminate, it's always going to work, by the way, guaranteed. You factor the top, you factor the bottom, and you cancel the factors that are causing the 0 on top and 0 on bottom, causing the indeterminacy. Okay, what does that mean we're actually doing graphically? Okay, it means we've traded our original function, which had a hole at x equals 1, for a new function. And what was that function? X squared plus x plus 1, right? That's the function that was left behind when we canceled those factors, right? What did that do? Well, it just created the same exact parabola, only it filled in the hole. Now we're able to apply direct substitution, right? We answered the question, where does the ant anticipate stepping on our original function? Trading our original function for an identical function that fills in the hole and actually evaluating directly to find out where he does step on the second function, right? Because where he does step on our simplified function corresponds exactly to where he anticipates stepping on the original one, okay? That's a lot of talking. Do you get the idea though? Give me a 1 to 5 on that. How we doing? Okay, all right, good. I mean, it takes practice. I mean, it's just you got to kind of wrap your brain around this stuff in calculus. It doesn't always happen immediately, but it happens. Okay, why don't you guys try one? I think that maybe is a good thing to do. Let's try one. You guys try that one. You want to go to? You can go to boards if you want to. Go to board work. You can do it at your desk. I don't care. Try this one though, and then we'll go through it. Okay, what do you always try to do first, by the way? Let's get in good habits here. When we're evaluating a limit, what do we always do first? Substitute. We try to evaluate directly so we can see which of the three things happens. What do we get when we evaluate directly? 0 over 0, so more work. Okay. Okay, real quick, I'll pause for just a second. So we get 0 over 0. This is a rational function, so it's a polynomial divided by a polynomial. So what strategy is absolutely guaranteed to work? We've got indeterminacy. How do we eliminate that? Go ahead, Ashton, say it again. The factor, right? So I've got a factor the top and factor the bottom. And already, you guys could tell me right now, what is the factor that has to cancel? X plus 3. And it's obvious because that's the only factor in the bottom. But even if it weren't, you could have told me that because as x approaches negative 3, what's the factor that would go to 0? Well, x plus 3, right? So just from even seeing what the limit is approaching, that's telling you that the factor x plus 3 must cancel. You already can anticipate what's going to happen. Now you just have to actually make it happen. Okay, so go. Try this one. Okay, what happened? What'd you get? Negative 5. Good. How did we get it? Okay, we factored the top. I can almost bet that if you wrote down work, most of you made one little mistake on your work that you didn't even know was a mistake. But here's what it is. I bet you that you didn't write down limit, right? Did anybody write limit? Good. Okay, that's good. Usually people don't, and I get it because you're trying to you know what's going to happen. You're going to factor the top and cancel some things. But when you're showing work on this, and like on the AP test, for example, during the open-ended part when you have to show your work, you would get marked down for not doing this, and I would too. When I look at your work on tests, if you don't include this, I will deduct some points. You haven't evaluated the limit yet, so you have to carry that limit notation along with you. Okay, this is until we actually evaluate the limit directly, we don't get to get rid of that limit notation. So this is equal to the limit of the top factors into what? X plus 3 times x minus 2. Okay, the bottom factors in, or it's already factored. So really, what did we do here? We just worked inside the limit. I want you guys to see that all the stuff I'm saying is completely consistent. We're going to do algebra inside the limit first to simplify what's going on inside the limit. So we took the argument of the limit and we turned it into that, which was a good idea because what cancels? The x plus 3's. Okay, so those guys cancel. And now we just end up with the limit of x minus 2 as x approaches negative 3. And now finally, we can evaluate the limit and be done. And we get negative 3 minus 2, which is negative 5. Good? Okay, congratulations. You just evaluated your first limit analytically. There you go. Okay. So let's go back and let's look at this example that we skipped over. What about something like this? Okay, now this is one where the algebra doesn't, we can't look at this algebraically like we did the rational functions, but we can still think about it analytically, right, in terms of what the functions are doing. It's helpful, though, to see these graphs, but we don't really need the graphs. If I've got the piecewise function, f of x equals the parabola x squared plus x plus 1 for all x not equal to 1, and it equals the value 1 when x equals 1, does everybody agree that's the graph we get? Okay. Well, if it's a piecewise function where the function is defined every place except 1 by this parabola, then if I want to use my strategy, what's the limit of f of x as x approaches 1? How could I trade that function f of x for a simpler one that's going to agree with our original function every place except at that one place where there's a deviation, where there's a hole in a point that's off the parabola? There you go, right? We're just going to essentially move that point up to there and fill in the hole by just looking at only the function of the parabola. Because again, the ant is going to anticipate stepping on our first function where he actually steps on the simplified function, right? So the limit of f of x as x approaches 1 is exactly equal to the limit of x squared plus x plus 1 as x approaches 1, which is what? 3. And that corresponds to what we see on the graph, doesn't it? Okay, give me 1 to 5 on that. You guys get our strategy there? Okay, man, you guys are doing great. Because this stuff is, normally, seems like normally it's a tougher jump than it seems to be for you guys. This is good. This is good. Not surprising to me at all, okay? And then here's just a little, for your notes, here's a little summary of what we just talked about, okay? So our dividing out technique or our cancellation technique, whatever you want to call it, same thing. Okay. This is just the graph that goes with that last example that we did. Okay, how about this one? If I evaluate directly, what do I get? If I try to plug in directly, what do I get? Let's see, negative 3 squared is 9, right? Plus negative 33 is negative 24, plus 24 is 0 over 0. So I do get 0 over 0, right? Okay, so then we have a rational function that's indeterminate, 0 over 0, so our strategy is guaranteed to work, what is our strategy? Okay, I got a factor top. What's top factor into? X plus 3, x plus 8 over x plus 3 as x approaches negative 3. Those guys cancel. And I would say you can even maybe, like what I've done there, I've canceled the offending factors. And so it wouldn't be the worst thing in the world if you just gave me an answer there, right? Because we can see those factors are gone. What's left behind? X plus 8 as x approaches negative 3. What's that give us? 5. Okay. Okay, what happens? Ooh. Whoops, I didn't mean for all that stuff to be on there. Let me get rid of. Okay, what happens if we have complex fractions? Well, we're always going to try to evaluate directly. No, we don't cry. No. If we evaluate directly, what am I going to get on the top if x goes to 0? 0. 1/10 minus 1/10. Bottom, I get 0. So this is again an example of more work. Okay, it's 0 over 0. So there's a couple ways we can go with this. And I thought, man, oh, there we go. Okay, yeah. So one way we could do this is we could just simplify top and the bottom and create a rational function out of this. Okay, so what would that amount to? I got to get a common denominator. What would I multiply? What's my common denominator going to be on the top? We're looking in the numerator. What's my common denominator going to be? It's going to be the least common multiple of the denominators, x plus 10 and 10. What would that be? 10 times x plus 10, yeah. So I got to multiply the first fraction, top and bottom, by, what am I going to do to this first term? I got to get a common denominator. So I've got my 1 over x plus 10. I've got to multiply both the top and the bottom here by what to get a common denominator? 10, right? Good. So I'm going to multiply both the top and the bottom by 10 minus, now the second one, I've got a 1 over 10. What am I going to multiply top and bottom by there? X plus 10. Right? That's just, just algebra. And then on the bottom, we've got an x, and we're taking the limit as x approaches 0, right? Okay, we good? Okay. So what's that give us on top? Well, we get a common denominator. Our common denominator is 10 times x plus 10. And then the numerators of both fractions and the operation that's connecting them, all that stuff goes in the top, right? If I write this with a common denominator, I'm just going to subtract the two numerators into the top, right? So I end up getting, in this big fraction on top, I get 10 minus 1 times x plus 10 is 10 minus x plus 10. Now this is one big fraction in the numerator. The bottom is an x, but I'm going to write that as x over 1. You'll see why. So then I've got to simplify that top fraction. My goal here is just to get the top into one big fraction, bottom into one big fraction. Well, if I distribute the negative on top, what do I end up with? What do I get in the top? 10s are going to cancel, right? I'm just going to get a negative x. So my fraction in the numerator then just becomes negative x over 10 times x plus 10, all divided by x over 1. Okay, well, if I divide a fraction by a fraction, I just flip and multiply by the bottom, right? So I could write this as a product of the top fraction times the reciprocal of the bottom fraction, like that, okay? But when I multiply fractions, I'm just multiplying straight across, right? So I'm really just doing that. Okay, so what has to happen here, if we go back to the very first step, what's going to have to happen somewhere in my algebra for this indeterminacy to go away? What factor is going to have to cancel in the top and the bottom? An x, because as x approaches 0, x goes to 0, right? That's causing the 0 over 0 that's messing us up. So now that I've simplified everything, look, it's going to cancel, right? I just end up getting the limit of negative x. I could write the bottom. Why don't I combine that x with the 10 over 10x times x plus 10. And now look at my cancellation. These x's go away. So on the top, I'm just left with a negative 1, right? On the bottom, the x is gone. And so this is equal to the limit of negative 1 over 10 times the quantity x plus 10. Well, now as x goes to 0, what does that become? Negative 1/100th, right? Because this guy, when I take the limit x goes to 0, when that goes to 0, that term just disappears, and we end up with negative 1/100th. Okay? So that works. I mean, one strategy, when you start off with complex fractions in an indeterminate limit, you can just turn the top into a big fraction, turn the bottom into a big fraction, and flip and multiply. And what you end up getting then, by the way, is we end up getting a rational function, just like the previous examples where we can cancel stuff. Okay, that's good. That works. Now, there is an easier way to do this algebraically. I'm going to show you a great trick. Okay, this is kind of a Mr. Roy special. This is a good one. For these, it's easier to just clear all fractions by multiplying both the top and the bottom by the least common multiple of all denominators, top and bottom. Okay, so if I look at the denominators on the top and the denominators on the bottom, look what we've got. We've got an x plus 10, a 10, and on the bottom, my denominator is just 1, right? I'm looking at the top fraction and the bottom fraction. The fraction, oh my goodness, what'd I do? The fraction in the denominator is just x over 1. So its denominator doesn't really contribute anything. But on the top, I had the denominators x plus 10 and 10. The least common multiple of x plus 10 and 10, you already told me, is 10 times x plus 10. Okay, so what we're going to do then is we're just going to distribute through this whole thing on the top and the bottom. We're going to multiply by 10 times the quantity x plus 10. I've just multiplied by 1. If I multiply the numerator and denominator by the same thing, I'm just multiplying by 1. So I'm not changing the value of this expression, right? Which I don't want to do. I just want to change its form, make it look better. Okay, so when I distribute this through, look what happens. When I distribute this whole thing through to the first term, I'm going to write it out this time, but in the future, we won't even have to. In the future, you'll be able to just kind of skip a step here. Look what we get. So we get the limit of In my numerator, I'm going to get 10 times x plus 10 over my denominator, x plus 10, minus when I distribute here to that numerator, I get 10 times x plus 10 over 10, all divided by, on the bottom, it's pretty simple. On the bottom, when I distribute to that one term, I just get 10x times x plus 10, right? Okay, look what happens here. What cancels in the first fraction? Look at that. What cancels in the second fraction? Way easier, right? Great trick. Thank you, Mr. Oya. That was a good one. So we end up with the limit of 10 minus the quantity x plus 10 over 10x times x plus 10. And that looks pretty familiar, doesn't it? I mean, we were there. It took us a lot longer to get there, but we eventually got there right there, right? Everybody see that? Right? If I just distribute the negative, we can see the work's all going to be exactly what we just did before. Isn't that easier though? So again, what's the trick? If we're taking a limit of complex fractions meaning fractions in the top and fractions in the bottom, you just clear the fractions by multiplying top and bottom through by the LCD of all the denominators that show up in top or bottom. When you distribute that through, you'll clear all the fractions immediately, and it becomes a rational function where you don't have fractions to deal with anymore. It just gets way, way easier. Okay? Give me 1 to 5 on that strategy. Does that make sense? Okay? Man, awesome. Okay, last one for today. What happens? So we've dealt with the easiest kind would be a rational function. Just factor and cancel the factors that are causing the indeterminacy. If you start off with complex fractions, clear the fractions and it turns into the first type. Okay. What about limits involving radicals when you have an indeterminate outcome? So if I try to evaluate this limit directly, I'm going to get square root of 0 plus 1. So square root of 1 is 1 minus 1 is 0 over 0. Indeterminate. Okay, any idea what you do? What in the world could we do there? Now let's think about this logically. What about this problem is really ugly compared to the previous problems? Square root. Yeah, we got a radical in there, right? So the part that's really ugly is this square root part, right? Okay, it wouldn't be so ugly if when we evaluated the expression with the square root, it didn't give us a 0, right? This would have been easy if x were approaching some other value. Like if x were approaching 8, it would have been way better. We would have gotten square root of 9, which is 3, minus 1 is 2 over 8. 2 over 8 is 1/4, done, right? Would have been a piece of cake. What makes it tough is that we end up with a 0 over 0, right? So we had this radical involved in an expression that went to 0, okay? So what we probably can't get rid of the radical completely, but our goal is to mix the radical up in an expression that doesn't go to 0 instead of one that does, okay? And the way we can do that is by multiplying top and bottom by the same thing. We have to multiply by a fraction equal to 1, but we're going to multiply top and bottom by the conjugates of whatever the expression is involving the radical, okay? So we're going to this is called a rationalizing technique. And if we multiply top and bottom, Good place to stop, huh? Okay, we'll pick this up tomorrow.